I'm going to focus on dwell mechanisms. By dwell, we mean having zero output motion for some non-zero input motion. Oftentimes, the way to do this would be with a cam and a follower. However, a cam and follower system can be quite expensive to machine and even to maintain at times. So instead, what we want to do is we want to generate a traditional linkage that is all revolute joints that has a dwell, and it's going to be an approximate dwell. This is not going to be a perfect dwell like you'd get in a cam and follower, but it's cheaper, it's easier to maintain than a cam, and it's also not hard to design. Our first focus will be on the single dwell linkage. There are two usual approaches to designing a single dwell linkage. Both result in 6-bar mechanisms, and both require first finding a 4-bar with a suitable coupler curve. In your textbook, in example 3.13, it shows how to generate a single dwell linkage using a 6-bar, and we're going to go through that example here, and then I'm going to show you doing the same in simulation using the force effect motion application by Autodesk. Here we have kind of the beginnings of a single dwell linkage. When they say use a 4-bar with a suitable coupler curve, by that we mean a coupler curve that has an approximate arc in it. And if you notice, the coupler curve that was chosen here, or the linkage that was chosen, has a coupler curve where right here along the top here there's an arc, and that arc is an arc that has been chosen because you can fit a circle at that location, and that circle's radius, which goes from about this point up to here, is approximately where your dwell will occur. I'm going to talk more about that. Usually what happens is you're looking for a linkage that has a curve, a coupler curve, where you can inscribe a circle. And so you can imagine turning to one of the tables in your textbook or online where there are symmetrical coupler curves, picking out one of these coupler curves that you know has a nice broad curve here where you could fit a circle. And if you were doing this on a computer, then you'd basically be taking circles and making them larger and larger, just seeing how much time or how much of their circumference would be used by this particular coupler curve. Your goal is generally to make sure that there is a dwell for a certain amount of crank rotation. So for example, in this first case, your coupler point, which in this case right here, is getting close to leaving the point where it is on the circumference of the circle. And so if you were to take this crank and move it back here, you'd find that this coupler point P would be moving along the circle. And so perhaps at theta 2 equals 90 degrees, perhaps this coupler point would be at this edge, and then at theta equals maybe 135 degrees, perhaps then you're nearing the end of the circular portion, and you're going to now go ahead to follow this path to come back around. So if you're starting at about 90 and then going to about 135, what you have there is about 45 degrees of crank motion. So for about 45 degrees or so of crank motion, you're going to be moving along this curve. That's usually going to be a metric, that amount of crank motion for which you can be on the arc. That's going to be a metric that's specified when you start doing a single dwell application. For this particular example, I believe we're going for a linkage that has a dwell for approximately 60 degrees, I think. Yeah, about 60 degrees of crank motion. And so I was saying 45, but this is probably closer to 60 degrees of crank motion. So this part here where you see the red curve, the coupler point probably enters this portion, probably not at 90, but somewhere further back, perhaps at 60 degrees or so. So what is done at that point, once you find such a curve. This curve will not always be found using the table. Sometimes this curve, or I should say oftentimes this curve is found in the Roans and Nelson Atlas of coupler curves. And I gotta go and show you a picture of that. This particular item is available on your course DVD. And I've taken one page out of that atlas just to kind of focus on here. And in this particular case, let's see if I can enlarge this a little bit. Here we have one page of this atlas. This atlas is filled with pictures like this. And what you see here is a particular linkage, right? And the crank, coupler, rocker, and ground link are all related here at the top, where they show kind of a scale, if you will, kind of how to go about reading this. And what it says here is that the crank is given a unit of 1. It's kind of hard to see right here, but the crank length has unit 1, and the coupler is given as A. It is going to be 3 times that length. The output rocker B is also going to be 3 times that length for this particular linkage, and the ground link is going to be 2 times the crank length. And so everything in this atlas is kind of driven based on the crank length. As you see, this is very similar to the one we were just looking at, where the coupler point lies along the coupler link, and that's a gamma of 180 degrees in this case, or 0 degrees. And what we'll see here is that when we place that coupler point approximately right here, which is about where it is in our example, that point's going to follow out this curve. These dashes, of course, again represent, you may recall, 5 degrees of crank rotation. And so what we are going for is about 60 degrees of crank rotation in this case, so that says how many of these dashes we want to see before we stop with one of the ones that we want. In this case, we're looking for about 12 dashes is what we'll find, for which we'll be at the point of being on a perfect arc. And so we can go here and go other places to find our desired curve. And as you see, there's many other curves that we could choose from on this particular page of the atlas. And so now I'm going to go back to those notes and pick up where we left off here, where we're looking at this example problem. And so once we found a arc that contains about the amount of distance that we need to get about this crank rotation, which is about 60 degrees of crank rotation in this case, we need to find the center of that arc. And we can do that online, in an application if we're placing circles here. And we can even do it on paper, though it's a little harder, of course, because then we're going to have to keep moving and maybe using stencils or something to kind of keep using circles larger and larger until we find the approximate circle that we need to be able to find the center point D. This center point, again, is going to represent the place of dwell. And in the second picture, we can kind of see that. I'm going to kind of make this picture a little bit bigger here. What we've done is we've added into this linkage a straight path where we're going to have a piston moving up and down, and we're going to connect a link from the piston up to the coupler point. And so what you can imagine now is as this link moves, as the coupler point moves along this arc, that point is not going to change because this is the center of that circle, this red circle here. And so during that period of time, from when the coupler point starts here and moves over to here, this piston is going to basically stay at that position. Now, once it gets past this point, of course, it's going to move down. And as you see, they show its lowest point here when the coupler point has gotten back around to this location. And so the piston then will be down here. And so this is our maximum stroke, and this is our dwell position here. And so that piston is just going to go up and down, and you'd expect it to come down, come back up, wait here as it moves along, as the coupler point moves along this path, and then go back down again. And so that's our dwell position, and this is our maximum stroke position. Now, just to say a little bit more about this, because it's going to look a little bit different in the final analysis. Usually, or let's say oftentimes, the output is not necessarily a piston output, but instead another straight linkage binary link like this output. And so there may be a link attached here coming over and have its ground position here. And so what you can imagine is as this moves up and down, you'd have that link pivoting at some point here. And I'm going to show you what that looks like as we go to the force effect motion application and see us create a mechanism similar to this with the dwell that we're looking for. So turning our attention to force effect motion, here I've put in the figure that we saw earlier, the linkage that has the coupler and the rocker having the same length, each of them about 3 times the crank length. And so if we go in here and look, we can see that our crank has a length of, actually I think I'm going to have to remove that, oops. Sorry about that. I have to remove that just to show you. So our crank has a length of 1. Decide just to leave it as 1, even though we know we can scale it. We can make it anything we want. And then we have 2 there before our coupler point C, 1 after. So we have a 3-unit long coupler and about a 3-unit long rocker. And our ground position is 2 units long. And so now if we put a motor here on our crank, we can watch this move. And we're tracing out a path that was about what we saw in the atlas. And so what we want to have happen is for this portion up here, right along this area, we want to find a circle and who has a center. We need to know where that center is because that is going to be our dwell location. Okay. And so using this, we're going to just go to some of this I've done previously. This was my first try at it. And I'm going to show you what that looked like. So in other words, I went ahead and I put in my straight portion here. And I thought the center of that circle would be about at that location. And so I went ahead and grabbed a link here equal to what I thought the radius of the circle would be. And I'm a little off, and you'll be able to see that because you'll never see the piston, which is here. You'll never see it rest. It's going to basically always be moving, which means I'm not quite at the center of the circle yet. And we can see that in a second here. And so you see point H moving. So it goes down. That's the maximum stroke. Then it's coming back up. And it should be stopped, but it's still moving, still moving, still moving. And it paused just for a second right over here. So that shows really that either my radius is wrong or my position of this straight piston, I guess, guide way is at the wrong location. And so my next rendition of this, the same thing. It's a little bit more careful trying to find the center. And I found the center this time to be a little bit further over. And this time we can see that we're going to get a lot more dwell this time for about the period of time that we wanted. And let's watch this. And so as you can see this time, there's our maximum, and we come up, and right there we're stopped. And we're dwelling. Now we're coming back down, maximum, and then here our dwell starts about right there and goes over to about here. And so that's pretty close to what we saw in the example in the notes. And so you can see there that we're getting a pretty good dwell. Now, what we want to do next is we're going to add this bar that's in there. We already have a 6 bar now, but we're going to add an additional bar, and we're going to let that thing be our output. And what we want in this particular case is we want a 90-degree output motion while we're in dwell. So the way that's done is what you need to do is you need to measure the distance between the dwell position and the maximum stroke. And so if we look at this, we can kind of see, let me go ahead and take this motor out for a second. What we can do here is we can kind of grab B, see if I can grab it. Sometimes it's kind of hard. And so right about here is where it's at its dwell position. And then right about there is where it's in its maximum point. So from about here to about here. And what we need to do then is measure that distance. And I've done that previously. And that distance measured out to be approximately 0.607 was the distance from the dwell position to the maximum stroke position. And if I want a 90-degree output, what I can do then is I can know that if I'm going to have some kind of extra link placed in, right, with some ground. Now remember, my piston is moving up and down here, right? And so this is where my piston is at its highest point, it's at its dwell point, and this is where it's at its maximum stroke, its lower point. If I'm going to connect a link here, get rid of the piston and just kind of have, this link goes up to that coupler point here. then what I really need is about half of the 0.607, so about 0.3035 or so here, the 45-degree angle here. That's going to tell me how far I need to put this ground point from that straight line position. And of course, if it's 45 degrees, then half of that 0.607 will be the same as this side. So my opposite and my adjacent are equal to the same. That tells me how far away to put my ground position. You can imagine that as I make this value larger, what's going to happen is this point has got to move in that direction. And so that point will get closer and closer. But since in this particular example that's in your book, they wanted 90 degrees of output, that's why I'm using a 45 and a 45 here. Okay, and of course this is not drawn to scale. And so what we'll see as we go forward a little bit here is I'm going to show how I kind of went about, and this is just another figure, just as this is very messy, but this is kind of showing how I went about trying to find a point that was a certain distance over and a certain distance over and a certain distance down to give me my position. And let me go to another one to show you my final rendition. So this is the actual final one, which shows it more correct. Let's just slide down here. I'm going to kind of zoom out first to kind of show you what we're dealing with. So we've gotten rid of our piston that was here, and we've connected in another link. And what we were looking for was this ground link location. How far was that going to be from the straight line where the piston used to be? And so let's zoom in, and what we have here is the dwell position, and we've come down and over the same amount to get a 45-degree angle. So this is about 0.303, and this is about 0.303, and we put our ground position. That's creating a 45-degree angle here. And when this thing comes down to its maximum stroke, that's the additional 45. So what we have there is we have this output link, therefore swinging through 90 degrees of motion. And now we're going to kind of scale down, and we're going to show that motion as that happens. So we're going to go ahead and let's see. I thought I pushed play. Let's see what's going on. Do I have something? Oh, I think this one is just for you guys to see. And I have another one that actually does it motion. I had to delete a few items that were helping me just to set it up to get it to the point to where it actually runs. And here we go. And so now we're in dwell, and see our line is not moving now. And now we're coming down. As you can see, we have our line moving. That's 45 degrees, still moving, still moving, still moving. An additional 45 degrees. Now we've moved 90 degrees, and we're at our maximum stroke. Now we're coming back. And we're going to be at dwell in just a second. Right about there, we're starting to dwell, and we're dwelling all the way to about this point. And so there we go. And you can see what's happening here. Now I know this is kind of messy. Let's see if we can zoom in here. Just kind of see more of what's going on there. And let it run again. And so you see here is our output rocker. You see here, this is the extra link that we've added. This is the thing that is of concern. We want there to be a 90-degree output from our dwell position up here to our maximum stroke position down here. And so we've got rid of our piston. In a way, the piston was just used to find that maximum stroke length. And then we're going to start moving down again. Moving back down. So 45 degrees we've moved through here, and now we've moved through an additional 45 degrees right about there. And so that shows really how to go about creating a single dwell mechanism. A few other points I wanted to make. There's also double dwells. And what I want to do is just mention that it's a little easier to design for double dwell in the one that I'm showing here. So we can also create a linkage with a double dwell. Some disadvantages of dwells generated this way is that the linkage gets to be kind of large, and there's some jitter during the dwell. So none of these dwells are perfect. All of them are approximate, and what we're saying there is in the example of our first single dwell, at this dwell location, this is not a perfect dwell. We end up with a little bit of jitter, a little bit of shimmy here when we're in the dwell position, because this is not a perfect circle that we found the center of here. We're going to get some jitter also in the double dwell. Now here's an example of the double dwell. What you're looking for in a coupler path or a coupler curve for a double dwell is a figure that has a double straight. And so here we have a straight here and we have a straight here. Here's our coupler point. And so what we're going to have in this particular case, as this crank rotates, this coupler is going to be moving along this path. Right? And then it's going to move here, and then it's going to be moving back down straight again. And so what we're going to use the fact that there's these two straights, put another link in here, and see that with another link and a piston, we're going to get a dwell at this location, and we're going to get a dwell at this location. And so here's an example of that. What we've done is we found kind of the center point of these two straights. And so we have a straight here and we have a straight portion here, and those two straight portions intersect there. That's where we're going to put a translation right here, a prismatic joint where we have a piston here moving back and forth, and it's going to move along this straight path. And as it's moving, of course, this link, this outer link, is going to be in dwell because this piston is moving straight along, and there's no need for this whole link to pivot at that location. But of course, once it starts to move along this path, this portion, this gray portion, will rotate up, and then when the piston gets up here and comes back down, it will be paused again. And so here we see the entire linkage kind of put together. And so again, our piston is connected to our coupler point here. And so as the crank rotates, and I guess they show the crank rotating in this direction, then that point P is going to be moving along here, in which case this outer link called link 6 in the drawing is not going to move. But the second that piston gets over here and starts to go up, we'll see this entire gray link move in this direction until it gets to be collinear with this line of the straight, this part of the straight, and then the piston is going to be moving down this portion, in which case link 6 again will be paused. And so really we're getting two dwells for one rotation of our crank. And so this is where we created a double dwell linkage. And that's all that I have at this time for dwell linkage design.